Hiya, it's Miss Blasky. We're going to start off a new unit, Unit 8, which is going to combine both thermodynamics and thermochemistry. For our purposes, there's really not much of a difference between thermodynamics and thermochem, but the big idea is that thermodynamics is talking about energy in general, and thermochemistry is talking very specifically about the energy transformations within molecules and bonds and how that affects chemical reactions. So first up, just some sort of review vocabulary. You should know all of this already, but just in case, it's all here. So we are going to be talking a lot about energy. So energy, the official scientific definition of energy, is the ability to do work or produce heat. We need to be able to differentiate between potential energy and kinetic energy. For our purposes in AP Chem, potential energy is the energy that is stored up, particularly in chemical bonds, but we could also talk about the potential energy of a spring or of elastic bands or things like that. Batteries are full of potential energy. Kinetic energy is the energy of motion. Again, in chemistry, when we talk about kinetic energy, usually we're talking about the kinetic energy of the particles inside of our system. So how fast those particles are moving usually is both controlled by how much energy is imparted to that system, usually based on heat or what we measure it as temperature. Big idea, huge idea in chemistry is the law of conservation of energy. We cannot be magicians. We cannot create energy. We cannot destroy energy. It can change forms. It can get transferred, but it's still there. This is known as the first law of thermodynamics. Some vocab that we'll be using a whole bunch as we're talking throughout this unit. There is a difference between heat and energy and temperature. So we need to make sure we're being very careful when we are talking about those things. So energy can exist in many different forms. We can have heat energy, we can have friction, we can have kinetic energy. There's all different forms of energy. But when we are specifically talking about heat, we are talking about how the motion of the particles is translated into the energy of that system. So we always talk about heat as the transfer of that energy from an area of higher energy to an area of lower energy, or from a warmer object to a cooler object. The heat transfers because of that difference in energy. So we're always going to get energy transfer from an object that is higher energy to an object of lower energy. Often we're going to talk about the difference between system and surroundings. This is pretty easy for us in chemistry. If you get into physics or some other sciences, sometimes defining your system and surroundings can be pretty challenging. For us, the system is usually whatever reaction is happening in the beaker. And the surroundings is the beaker and the air and our hand and anything else outside of that chemical reaction. Reminder about the difference between endothermic and exothermic. We're going to be talking about this a bunch. If you are endothermic, that means that heat is going into that system or going into that chemical reaction or into that chemical species. Exothermic means that energy is being released overall. It's been a while since we've looked at these energy diagrams. Back when we were doing kinetics, we talked about this, but these are going to come back where we've got our reactants starting at the beginning, our products at the end, and we can follow along that energy pathway and see how the energy is changing as that reaction occurs. Remember the height of the hill, this is our activation energy. The difference from reactants to products, this space is the heat change of the chemical reaction. So in this particular case, my products are ending at a lower energy than my reactants. So this would be an exothermic reaction because that heat is being released. I'm ending at a lower energy than I started at, which means that heat needed to go out of the system. If my graph was the other direction, if it ended up like this, then that would be an endothermic reaction, because I need to end with more energy than I started with. So that energy needed to go into that system. So being able to identify whether things are endothermic or exothermic is pretty important. Take a look at example 1 real quick. Being able to identify both the terminology and where that energy is flowing. So part A student conducts a chemical reaction in a test tube and feels that the test tube is hot. We need to identify our system would be the test tube. Our surroundings would be the student and that student's hand touching the test tube. If it feels hot, that means the energy is flowing out of that test tube into the student's hand. So that would be an exothermic reaction, which means that energy is flowing out of the system. B, mix two chemicals and we see some frost appear on the outside of the beaker. That means that my beaker itself is lowering in temperature. Now this is sort of weird. If it is lowering in temperature, which way is the heat going? If I touch it, it's going to feel cold, which means that if I touch it and it feels cold, heat is leaving my hand and going into that system, which means that it is an endothermic reaction and energy is flowing into that system. Now, where is that energy going? Now, we talked about that there's multiple different types of energy, right? So that energy flowing into that system is not necessarily going to heat up that system. It's obviously going into doing something with the bonds or rearranging molecules or doing something along those lines so that it keeps requiring energy to go into that system. So C, the temperature on a thermometer drops when placed into a test tube that contains a reaction. So again, identifying our system and our surroundings. We could talk about the thermometer or we could talk about the test tube. Because technically the thermometer dropping means that feels cold, which means that heat is flowing out of the thermometer and into the test tube. So we could talk differently about whether we're talking about the thermometer or whether we're talking about the test tube. Let's talk about the thermometer. So if we're talking about the thermometer is losing heat. So it is exothermic. Oops, sorry. If the thermometer is our system, right? It means energy is flowing out of that system. I was right. So it was exothermic. I thought they were in a different order. If we want to talk about our test tube from the thermometer, heat is flowing into that system. And so it would be endothermic. So it really matters what we're talking about as our system and as our surroundings. So just being able to identify whether energy is going in or coming back out is important. Now, we also can do some calculations with our enthalpy measurements. We'll talk more about all kinds of different things we can do with enthalpy calculations. Enthalpy is our fancy word for heat. So enthalpy is represented by the variable delta H. So delta means change. Remember, when we talk about heat, we're always talking about a movement of energy. So we're talking about how that energy has changed in a system. When we're talking about chemical reactions, we take the energy of the products of that reaction, subtract the energy of the reactants of that system. And like I said, we'll talk more about why it particularly goes in that order in a little bit. But first, we just need to talk about knowing a delta H and knowing what that means. So again, this should be review. If delta H is negative, that means that the reaction is exothermic. If delta H is positive, then the reaction is endothermic. So thinking about what process is going on, we should be able to give an idea about which things have higher energy, which things have lower energy, and how that would require us to change our processes. So for example, in example number 4, deciding whether these are endothermic or exothermic reactions. If I am taking solid potassium and trying to turn it into gaseous potassium has a lot more energy to it. So in order to make this change, I would need to put energy into my system to break up some of those intermolecular forces that a solid has to form that into a gas to give those particles more energy. So this would be an endothermic reaction. We haven't talked a whole lot about removing electrons recently, but if we think way back to ionization energy, remember, is the energy required to remove an electron from a system. So removing an electron would also be an endothermic process that's going to go in. Most of these are endothermic. Here we've got chlorine gas, which is diatomic, and we want to break those bonds between those chlorine atoms and form just chlorine atoms instead of in the molecule. So in order to break bonds, we have to put energy in. So that also is going to be an endothermic reaction. Chlorine gas gaining an electron to form chlorine ion. This is the opposite of ionization energy. This is putting an electron onto things. So it's going to have the opposite sign for energy. It's going to be a negative or an exothermic reaction. We're actually going to be able to generate some energy that way or release some energy. And then taking potassium ions and chloride ions and forming solid potassium chloride. Again, we're looking at gaseous particles going to a solid. Solids have much less energy. They have a lot more intermolecular forces holding those molecules together. And so we're going to be forming some interactions, making things a little bit more orderly. So that is going to be an exothermic reaction. All the energy that those gases had, we're basically settling those molecules down into a solid. So they are going to release energy. Pretty much all of the time in this class, we are going to see this little delta H at the end of a chemical reaction. So this is going to tell me about whether this particular chemical reaction, the way it is written, whether it releases heat, whether it requires heat, and how much heat it releases or requires. We're mainly going to be seeing kilojoules here, so we need to make sure that we can remember that unit there. For this particular reaction, we are be able to release 91.8 kilojoules when this reaction occurs. Notice that the coefficients this way are written particularly. So if all of a sudden, instead of forming 2 moles of ammonia, I formed 4 moles of ammonia, I would double the energy formed in this reaction. If I only made 1 mole of ammonia, I would halve the amount of energy made in this reaction. We also could talk about reversible reactions. This particular reaction is not super reversible the way it is written, but we could turn this into a decomposition reaction. We could take ammonia and decompose it. Since delta H is negative the way it is written, to form ammonia, we get an exothermic reaction. If we switch this around to the decomposition reaction instead, that would just flip the sign on my enthalpy, on my delta H. So I would have to put in energy. It would be endothermic to decompose ammonia down into nitrogen and hydrogen. So we can do some stoichiometry, some mole relationships with this energy amount. So example number 5 is already worked out for you. We're talking about combustion of butane. Butane gas is what's in most household lighters, like to light candles or your grill. Says highly exothermic process releasing 2,845 kilojoules of heat per mole of butane. Pay attention to that. That's going to be important. Write the balanced thermochemical equation using all whole number coefficients. Also determine the enthalpy change by burning 50 grams of butane gas. So if I write out this balanced equation, I've got here butane reacts with oxygen, forms carbon dioxide and water. Change the coefficients around in order to get that balanced. Notice that when I put my coefficients there, I have to have 2 moles of butane. Otherwise, it's not going to balance out. That is going to mean that I have to double the heat released, because it says I released 2845 kilojoules per mole of butane, but I've got 2 moles of butane being burned here, so I need to double that. So sometimes you might see it written that way. Sometimes you also might see that specifically said that you wanted to use whole number coefficients, but you might see cases where you see fractional coefficients like this. Even though it's not convention the way that we're used to, it still is possible to write it that way, especially when we're talking about enthalpy. Because they'll probably write it this way and say delta H is negative 2845 kilojoules per mole. So that's telling me that for 1 mole of this, or for 13 halves of a mole of oxygen, that's the amount of energy released. Notice that they also wrote in negative signs because we specifically know that this is exothermic and it is releasing heat. So we need to identify that with a sign. And then we can do a little bit of stoichiometry by saying, well, if I have 50 grams of butane, I can figure out how many moles of butane that is. Molar mass of butane is 58.14 grams. I get 0.86 moles of butane. If then 1 mole of butane released 2845 kilojoules and I only have 0.86 moles, I can figure out how much energy I released for my 0.86 moles. So again, it's just making sure that you're reading that question really carefully, that you're paying attention to the units, and what that is referencing in our balanced equation. Right? I'm going to stop there for right now. There's a couple more examples about doing this stoichiometry and how delta H relates to chemical reactions. We're going to work on some of those in class. So I will see you all later. Take care.